Hi, this is Crossdot and Nabla, and in today's video, we're going to be covering over section 12.4, covering over partial derivatives. And before I even start going through the notes and explaining the ideas of partial derivatives, one thing I like to say about this section, it's probably one of my most favorite and probably one of the most intuitive parts of Calculus 3, and it will appear intuitive to you as well as we go along. So part of the issue with having standard derivatives in multivariable calculus is that what does that look like? What does that mean? We think of derivatives in one variable, in single variable calculus, as just being a change in y over a change in x, right? An infinitesimal change, right? So it's usually gonna be like it's gonna be something like dy dx, right? But in multivariable calculus, it's a little bit different because we're changing over x and y. We're not just changing over one variable, we're changing over two variables at once, right? And that's something we have to be conscious of, right? And rather, instead of taking a derivative, you're taking a partial derivative with respect to a single variable while holding another variable constant. In single variable calculus, for example, let's say we had this function y equals 3x squared, right? In essence, we're holding that 3 constant because it's not changing. It's changing the graph, yes, but it's not changing the actual derivative process, right? And we get y prime or dy dx or f of f prime, right? Whatever notation you use, you get 3 times 2x to get 6x, right? That doesn't change. In multivariable calculus, however, you're treating the variables like y or x. If you're taking the partial derivative with respect to a different variable like x, you're keeping y constant. Y's like a constant like 3 now. And part of this idea will be shown with this visualization right here, right? We're cutting the same surface, but in two different planes, right? And we have our point P not right here, right? Right here. And we're slicing it across a different plane, right? And planes we've covered in one of our earlier sections. What we're doing is we're just treating, in this case, example 1, a certain y value constant, because this is going to be x, y, and z, right? We're holding y constant, and we're just looking at the x. Then you can get the slope of a tangent line there. Then you can get the slope of the tangent line for a b. You can get the change in z over the change in y, right? Because you're holding your x constant. And this is why having derivatives in calculus 3 or multivariable calculus is difficult. You can't just say that you have a derivative because it's changing, because a function is going to be changing across multiple variables. It could be in terms of y, x, or z. It could be in terms of y and x, right? And that is why we use partial derivatives instead to notate that. Because you could be saying, taking the derivative of this, well, that's kind of vague. What does that mean, So we use partial derivatives instead to notate that, right? And each of these curves have a tangent line as well. That's not something that's changed, but rather, in this video, actually, we'll show how we can translate these partial derivatives from 3D to just being standard derivatives in 2D, right? That's another important topic as well. And one last thing to note, that each tangent line has a steepness associated with it. And that makes us think of the slope of a tangent line in single variable calculus, right? And we'll cover that. And then we have our standard limit definition of the derivative. We have multiple variables now, x naught plus delta x, as delta x goes to 0. Same thing with delta y going to 0. Those things are kind of familiar. If we remember our f prime of x notation, where it's like f of x plus h, like this, limit as h goes to 0, or delta x, it doesn't matter, right? One important piece of notation that you guys should be familiar with is seeing this f sub x, f sub y. And this is paramount to having an understanding of partial derivatives in this course, right? Because it's different than saying dy dx or df dx, right? that is a fundamentally different thing because this statement right here is assuming, the assumption is that you only have one variable. You only have one variable that you're differentiating with respect to. And we'll cover that notation down here on the next page or so. But it is absolutely imperative that if you are on an exam or you are doing practice problems, if you are covering over partial derivatives, the number one thing you should be conscious of is writing it like this, the f sub x, f sub y. And it'll be important later on, and we'll show it at the bottom of the next page, right? But example 1, we'll just walk through it together because I think this one will help ease up any stress that you guys may have had, like, oh my gosh, this is like a really difficult concept. Rather, it's applying your knowledge from Calculus 1 of taking derivatives in single variables, just treating like x and y like constants. It's a little bit unintuitive at first, but once you understand like the process, it's a lot of like, it's very mechanical. You have to go back and forth, right? It's not that bad. So we're taking the partial derivative with respect to x at 0, 3, partial derivative with respect to y at 0, 3 for this function, right? If you want to try this on your own, feel free to pause the video, and let's get right into it. So f sub x, let's just get f sub x first. Y squared is a constant here. These are all constants with respect to x, right? So we're going to just leave that as that. So we're going to do 3y squared times 2x. These are constants that go to 0. F sub y. We have x now is a constant, so we can just leave the x out front. Then we have 12y squared. And then the 5 just is also a constant with respect to x and y, right? That's not going to change. Now we can actually evaluate these at their respective points in space. Goes to 0. And this goes to a value that I should be able to derive really quickly. And this is kind of tedious, of course, but a lot of the basics are tedious, and we get our results 0 and 108 for f sub x and f sub y. You can say that take the partial of f with respect to x, take the partial of f with respect to y. You can write f sub x when we have other notations down below to show. And these types of notations are going to matter a little bit depending on if you're going to have to take the chain rule of a composite function, right? And we have our new notation right here. We have this. If we know that z equals f of xy, if it's explicitly defined, right? Because there's a difference between it being explicitly defined and implicitly defined like this. And we'll cover that in our later videos in this chapter. This is implicit, explicit. We take the partial of f, take the partial of a multivariable function f with respect to x. We get del, not d, del. This is a del, and this is another This is kind of similar to taking d dx, right, or dy dx. However, this del symbol, like this, indicates that you're taking a partial derivative. You're not taking a normal derivative. There's not a normal derivative per se, but that's what we'll use in this case. It's not like a single variable derivative because you have multiple variables changing x and y, but you're holding y constant, and you're taking the partial with respect to x, right? And that's what the notation says right here. Partial derivative of f with respect to x, partial derivative of f with respect to y, right? In example 2, we have z equal to this. Find del z, del x, and del z, del y. And one important thing I will mention, and this is a kind of being a stickler about notation, is that if you write dz, dx, and dz, dy, but it's a multivariable function of x and y, you are going to lose points on your exam. because it is a fundamentally different thing, right? That's one thing that's really important about this section, being careful with your notation, right? So if you want to try this example on your own, feel free to pause the video and let's get right into it. So we got del z del x. Just take the partial first off. We got y constant, so we're going to get 2xy plus derivative of this, we're going to get minus sine xy. Take the derivative of xy with respect to x, we get y, which we can rewrite as 2x minus y sine xy. And if you are going through more and more of these problems, you're going to realize that the treating variables like constants will become my second nature. It's not too terrible to wrap your head around. In this case, del z del y. Let's make that more clear and unambiguous. Del z del y, this is going to be x squared plus, actually x squared minus sine xy. Take the derivative of xy with respect to y, we get x. So then we get del z del y equal to x squared minus x sine xy. In example 3, we have to find the slope of the tangent line to the curve of intersection of this surface. 3z equals 36 minus 9x squared minus 4y squared. And this is the upper half of an ellipsoid. And you can check for yourself as one of the quadratic surfaces, but it's kind of easy to identify, right? And we have to be conscious of both the plane, the point, and the surface. And when we say finding the slope of the tangent line, we mentioned earlier that that slope of the tangent line is a little bit more ambiguous in this case. But now that we're focusing on one variable, we're holding x completely constant with a value of x equals 1, right? That's what we're referring to now with slope, right? And if you want to try this example on your own, feel free to pause the video and let's get right into it. So first off, we have to get in terms of z equals f of xy, right? So we're going to do z equals, let's actually just write it like this. 9x squared minus 4y squared to the 1/2 over 3. And then let's just do del z del y. We're holding x constant. So we're going to get this down here. We're going to get 3 times 36 minus. And then we're going to multiply by negative ay right here. And we forgot our 2 down here because it's the chain rule of the exponent, right? And then we got this. We can rewrite it like this. And then we want to evaluate it at our point 1 comma negative 2. 1 comma negative 2. So then we're going to get negative 4 over, negative 4y, I forgot about that, yeah. It's important to remember that because, yeah, we had it up here as well, yeah, so silly me. 36 minus 9 minus 4 times 2 squared is 16. So this is going to be 8 over 3 root 11 as our slope. And we can actually write this in point slope form as well. And we can do that real quick. Instead of it being y minus y1 equals m times x minus x1, it's going to just replace y with z and then x with y, right? So we can do that real quick. We get z, we get z minus root 11 over 3, right, equals a over 3 root 11 times x, not x, excuse me, y minus y plus 2. Oof. And if you want to check this on Desmos, we will be going to check that to verify that this all looks true and above board, right? Okay, so now we're on Desmos, and we're looking at our function, right? And it's a little bit choppy because Desmos does a little bit of weird rendering sometimes, but that's okay. What we're really concerned about, though, is looking at our graph at x equals 1, right? And we're doing a splicing at x equals 1, the plane x equals 1, right? And this is what the shape is generally going to look like, right? And if we go down to here, we have our 3D curve, but just in 2 variables now. We have it in terms of y and z, right? And now we can see, that kind of rhymed, but didn't intend it to, but now we can see that we have our slope of our tangent line right here. And that is how that would look in terms of the change in z over the change in y, right? And you can see that's perfectly tangent over that curve, right? And that's one of the beautiful things about this, actually, is that you can, if you want to scale it up from 2 variables to scale down from 3 variables to 2 variables, excuse me, you can do this by just holding a single variable constant, right? And we held x constant, and we set x equal to be 1, right? And that's a pretty cool thing you can do with this. Now, in example 4, we're given the temperature in degrees Celsius on a metal plate and the xy plane is given with this function. What is the rate of change with respect to the distance in feet if we start moving from 3, 2 in the direction of the y-axis, right? So if you want to try this example on your own, feel free to do so. And let's get right into it. So when I imagine this problem, right, these are some real-world applications of partial derivatives, right? If we're moving in the direction of y, we have a change in temperature with our change in y. I'm going to go with taking the partial derivative with respect to y, right? So we can do like del t del y or t sub y. Either way, it would work. I'll just do t sub y. Doesn't really matter, but we can get 3y squared as our partial with respect to y. And we can check at 3, 2 to be 3 times 2 squared. There's no x component in this partial, so we're good. And then we can get 12 feet per Celsius. Oh no, I think that's 12 Celsius. 12 Celsius per feet. Because it's a rate of change of the temperature right here. So we have, and this actually works better with the del notation instead of the subscript notation, where you know that this is going to be some d delta Celsius over some, actually let me write this in red because I think it's easier to see. Delta Celsius over delta feet. And that ultimately gets you your units right there. Pretty nice. Higher order partial derivatives. So this is something that shouldn't seem too bad. It's just, again, taking the chain rule, right? The f sub xx, f sub yy, those both should be relatively straightforward. It's the f of xy that may seem confusing. And one thing that is important to know is for the f sub xy and f sub yx, the order does not matter. You could actually flip it to be f of xy equal to f of yx. And this problem right here would actually show this. Find all 4 second partial derivatives for f of xy equal to x cubed plus y squared, all raised to the 5th. If you want to try this on your own, feel free to pause the video. Let's get right into it. Okay, I'm going to get my f sub x and my f sub y first. That's what I usually like to do with these types of problems. Okay, And then I have, let me just lift it up a little bit. Let me just write it right here. Okay. So I'm gonna do 5, I'm gonna just do this, multiply by x, derivative of x cubed. Just let me get that. Okay, and then f sub y equals the same thing. So 5 times that plus that times 2y. F sub y equals 10y. And that was only the first partial derivative. It's gonna get kind of crazy afterwards. So I'm going to do this. I'm gonna do f sub xx now. This is gonna require some chain rule, so just be prepared for that. Some product rule actually also. So 30x, like that, keep that constant, plus 15x squared times 4 times 3x squared times this entire quantity right here. And let's just ease this up for myself. 60, 180. Yeah, so let's just do this real quick. And again, this is a lot of like very mechanical, like quote unquote boring math, but I still think it serves its purpose in applying the topics of knowledge that you guys should be learning in calculus 3, and that should be A3, as I just said that. And then we can put a red box around this. This is the answer you should be getting. Actually, the answer you should be getting is this right here. You could simplify this if you want. I'm not going to. Maybe for some of the other ones I will, but it's just too much factoring for my liking. Okay, so we get 10 times this entire quantity. And for me personally, it's kind of mindless, and it's not not that it's not like challenging. I mean, math can't always be challenging, but it's the ability to just do it kind of aimlessly is my favorite part of the class, or just in math in general. And I can just leave it like this, actually. I don't have a preference of doing any more. And now let's get to f sub xy and then f sub yx. And let's actually copy paste our results down here. Then because I don't want to rewrite that entire thing on my own time. It's just not worth it for myself. And then we're going to get to f sub xy equals 15x squared, because that's a constant with respect to y, remember, times this whole quantity, raise it to 1 less, multiply by the inside, and then multiply by 3. Oh, no, this should be 4. Yeah, that should be 4. So then we're going to get 120x squared y times this entire quantity. x and that. And then same thing for this, just take the partial now with respect to x. Y is a constant with respect to x. And then we can do times 4 times 2y. Oh, no, not times 2y, times 3y squared, 3x squared times this entire quantity. So it's going to be 3 times 4 is 12. Multiplied by this whole quantity equals f sub yx. And those are your 4 partial derivatives. And as you can see right here, we just kind of showed an example of how the partials with respect to x and y, so f sub xy and then f sub yx, they're equal to each other. And that'll save you some time. If they ask you to solve for all 4 partial derivatives, you only have to solve for 3, unless your professor specifies, right? And that's like a nice, cool shortcut that pops up from partial derivatives. We have 2 more examples to go. And this one is going to have you recall on your inverse trig knowledge. And I'll just rewrite that formula right here. So if it's like you're taking the, just say f prime of f prime of tan inverse, it's going to be the derivative of inside 1 plus inside squared, right? And we'll just go through the first partials real quick, and then after, feel free to pause the video if you want to, or you can pause the video right now. Let's jump right into it. All right, this is going to be kind of a beast to solve. It's going to be involving a lot of tedious chain rule stuff, so we can still get through it. I'm a believer. So we have f sub x equals y 1 plus xy squared. The reason why we're doing that is because xy goes here, and then the derivative of xy with respect to x gets us y. And then f sub y equals this quantity. And now we can get into our actual partial derivatives. And one thing I will do before I even start is I'm going to rewrite it like this. Just going to save me time to like even think. Now we're going to get f sub xx equals negative y times 1 plus this whole quantity to the negative 2 times the derivative of the inside, which is going to be 2xy squared. So then we're going to get negative 2xy cubed all over 1 plus xy squared equals f sub xx. And then f sub yy, we can actually just box this in as our first partial derivative, and we have 2 more to go to solve, but 3 more to get the answers for f sub yy. Let's move it a little bit over here. Let's rewrite it the same way because I am not going to be doing quotient rule. I am not a fan of the quotient rule at all. And then we have f sub yy equal to x times negative 1. We can just write actually negative x times 1 plus xy squared times 2x squared y. And then we get f sub yy to equal negative x, negative 2x cubed y all over 1 plus xy squared. And then that's our answer for that. Now we're going to have to get to the more difficult ones that involve the product rule, because before it only just involved the single variable that you're differentiating with respect to. So let's just move this down here. Let's move this other one down here. Saving myself some time, honestly. I cannot be bothered to rewrite the same thing over and over again. And let's get back to f of xy. We can rewrite this as y times 1 plus, not f of xy, it's f prime, f sub x still. And then now we can get to f sub xy equals 1 times y, negative y, 1 plus xy squared to the negative 2 times 2xy squared. And that should get us our result right here. So f of xy is going to be this, and we're going to get 1 over 1 plus xy squared minus 2xy cubed all over 1 plus xy squared squared. And if you feel bothered to have the same denominator so you don't have to deal with this clutter, you can feel free to do so. But I would rather not, but I'll still show it for the sake of clarity in this problem. So we'll just do this. And I keep on saying this throughout the video, but I still feel like it's important to mention that this is a very mechanical process. But that's probably one of my favorite things about this section, or this topic in general. It's very mechanical, it's very boring and plain, but it's just so satisfying if you get the right answer. And if you don't get the right answer, it's really irritating to say the least. And this should actually, did I make a mistake somewhere? It's supposed to be 2x squared y squared. I did. Yep. This is supposed to be 2x squared y, yeah. Yeah. That's what I thought. Yeah, that made sense. Okay. Because here, when you get to here, you're taking the partial with respect to y. So it's going to be 2y, not 2x. Yeah, perfect. And then we can go here, and we can get 1 plus x squared y squared minus 2x squared y squared all over 1 plus xy squared squared plus f sub xy, which also equals f sub yx. That was probably the longest part of this entire video, but that's okay. And then for example 7, we have this function right here. I'm not going to be bothered to read all of it out, but if you want to pause the video and try this on your own, feel free to do so. If you're concerned about the z, it's just like any other partial derivative we've taken so far. It's not the end of the world, right? Let's just jump right into it. So for f sub x, we have y squared minus 2 over yz plus 3z squared, red box over it, f sub y. Let's move this a little bit down, actually. That's what I'm feeling like right now. We have 2xy, and I'm going to rewrite this as negative 2x yz to the negative 1. Okay, you can take the partial of that with respect to y, so it's going to be
negative 2x times negative 1 times z yz to the negative 2. Okay, so then we're going to get 2x, we're going to get plus 2xz over y squared z squared. And then you're going to get this to become f sub y equals 2xy plus 2x over y squared z. That's our second partial derivative down. F sub z, because there's no, f sub z, the first term's constant, the second term we have to do the exact same thing, but we can just replace the x with the z on the top. Just kind of cheating, but all is fair in math. And it's supposed to be 2x. Let me just make sure 2x. Oh, we'll actually double check just to be sure. Negative 2x yz to the negative 1. 2x times yz to the negative 2 times y. Yeah. Plus 9z squared x, our partial with respect to z, and then we have to take the partial with respect to z for the partial of x. And let's just bring down our result right here. Nice thing about having an iPad and recording these videos on the iPad is that this is a nice little shortcut I can just take. F sub xz equals this. This is going to be 0. And this is going to be, we can just write this as negative 2 yz to the negative 1. Take the partial of that with respect to z. We're going to get 2 y over yz, which is just 2 over z. I believe. And then we're going to get plus 9z squared for that. That's our new partial. And last but not least, we have to take the second partial with respect to y. And let's just jump right into it. Let's just copy and paste this over. Again, saving me and use a little bit of time. And let's just clean this up, rewrite it as 2xy plus 2x y squared z. F sub yy equals 2x, because 2x is a constant with respect to y. And we can rewrite this whole thing as 2x over z y to the negative 2 like that, because these are all constants with respect to y. So we're going to get this to be minus 2 times 2x over z y cubed in the denominator. And we can clean this up to be f sub yy equals 2x minus 4x over zy cubed. And that is pretty much it, covering over this section of partial derivatives. Probably my favorite in this entire chapter. Thank you so much for watching, and I hope you guys have a fantastic day.